Meet Pete. Pete doesn't know it yet, but in 3 hours and 41 minutes at 7:43 a.m., he will be rushing his pregnant wife Abby to the hospital. He won't be thinking about whether his car is charged and able to safely cover the distance from here to there, because the engineers who designed and built Pete's car already thought all about it. SAE International assembled a team of engineers from all over the world to think systematically about the charging of Pete's car. These engineers developed a series of standards that made mass production of Pete's car safe, affordable, and environmentally sustainable. But Pete won't have to think about any of that. He's probably never even heard of us. And we're fine with that. Because in helping the engineers keep Pete's car fully charged and safe, we've done our job. Sleep well, Pete.
Welcome, everyone, to the development of a battery-boosted EV charger. I'm Stephen Chung, CEO at ReJoule, and we are partnered today with SAE Detroit section to bring you this discussion. Today, we are going to address the development of a battery-integrated high-power vehicle charger and its implications on the health of batteries. It's an honor to welcome the first presenter on this topic, my friend Anurag Kamal, CEO of ElectricFish Energy. Anurag, welcome.
Thanks for such a kind introduction, Stephen. Hello, everyone. Today, the title of our talk is how we went ahead and development of a battery-boosted EV charger, rather an extreme fast charger, and what did it take, what were our learnings, and what is the user experience which we're trying to bring to a user. Mostly talking about the story, vision, and the product of the company and the recent pilot, which we did, will be the first part of my presentation. Then we talked about what is XFC, extreme fast charging, and why is it super important to limit the session length of these fast chargers. Then we'll bridge the conversation down to how exactly fast charging affects the battery health. And then I'll pass it over to Stephen to talk more onto that. So the company itself, ElectricFish, is a startup based in Silicon Valley, California. We have 4 co-founders, mostly coming from the domain of first just EVs itself, mostly from industry as well as academia and national lab space, more of energy optimization backgrounds, and also developing software systems at places like NASA. So starting with the big problem, how exactly we started thinking about the company was what we're trying to solve is, number one, is to make sure that we have all our electricity coming from renewable resources. Now, these resources are intermittent in nature, so you must build a lot of energy storage so that you can store that energy and use it later, both for powering your homes as well as powering your transport. And the second thing is that going all electric on EVs. This means that we have to build a lot of public fast charging infrastructure. Public charging and fast charging EV draws power worth hundreds of ohms. This is not something the grid was designed for. So we have to find and do some innovative ways to build this infrastructure. And then finally, the electricity grid's reliability is dropping all across the US. And if our homes are out of electricity, we don't want our cars to be out of electricity either, because that will be a truly disaster scenario. The product which we built is designed to solve all of these problems at the same time and can scale much faster too. The 350 square, it's a box which is roughly size of SUV, if you will, and it does not require any specific permitting, trenching to drop and install. You have to work with AHJs, that is the fire marshals, if you're doing it in a public location, but it works with a low voltage electricity grid, something which is readily available at a local business like a gas station, a convenience store, or even at some specific homes. But drawing just energy like a business, we can still deliver gas-like charging, delivering up to 140 miles of range in just 7 minutes. And it has also enough backup power to charge up to 15 cars, even if the electricity is out, delivering up to 100 miles of range. The backup power can also be used to power homes, up to 40 of them for up to 5 to 6 hours. So it's truly a resilient solution, which is built around storing renewable energy and discharging to cars and homes very fast. The tech stack is pretty simple, right? We do have a patent on it. The energy from the electricity grid is coming in through a bidirectional AC to DC converter, generally a single phase one, so that we can store energy when we think it's wise to do that, using some grid data, which is generally real time, figuring out where exactly when there is a lot of renewable mix, that is when we store energy from our AC to DC converters to our big battery pack. This battery pack is directly connected to a DC to DC converter. And this DC to DC converter works with EVSE communication chips to actually modulate that voltage so that we can actually charge cars from anywhere from a system voltage of around 250 to 950. There are multiple considerations in the system stack. Obviously, you have to choose a specific battery pack voltage so that you can choose a topology of a DC to DC converter. Is it a boost? Is it a buck boost? Is it just a buck system? The high voltage means you need to spend a lot on making sure the system is safe. A low voltage system means that you have to go so low so that you can always boost it up, which increases the current to significant amounts if you're doing a 350 kilowatt charger. So yeah, we have iterated over it, chosen a system voltage battery pack, and besides the hardware, we built more things to augment it, because our solution is not to just sell hardware or provide this as a hardware solution to most of the businesses. Our goal is to build a network of these units because we see that the long-term value of this network comes from inclusive ownership. So this hardware, when it was built, which can provide EV charging as well as work with the low voltage electricity grid, and also can be moved around seasonally. We first built this tool called Core Score. It's another patent which we have. It's called the Community Resilience Score. It uses specific data sets and evolves over months, in which we are trying to make predictions on where exactly are the most worst locations where it needs much more backup energy. We use capacity like data like hosting capacity, where exactly the grid is weak, what is the probability of an outage based on climate disasters or historic data, and also socioeconomic indicators, so that we are making sure that the access of EV charging and backup energy is distributed with equity. We go ahead, figure out where exactly these units need to be deployed. We go sign a contract and drop the unit there, and then have an optimization onto the top, which is continuously running real time, making a prediction on where exactly the energy needs to be allocated. Are we storing that energy for EVs, which are going to come at our deployment that day? Are we storing that energy to participate in grid resiliency services, that is making money from the grid, or preparing for an eventuality in which the grid might be off during that time? Generally, that prediction is there, in which we can prepare at least a day ahead. And then we collect that data, feed it back to the core score, keep improving it, and that's the whole cycle of products which we're building. The pilot which we did last year to March of this year was to deploy our first unit. It's a 210 kilowatt hour unit, which can still do 350 kilowatt charging. We were able to deploy this unit in just 2 days. Just shipped it from San Francisco on a 14,000 GVW truck, drop it, activated using a single phase connection, and it was ready to go. Because we were just working with a single phase 20 amp connection, we could only do 5 charging sessions per day. But that basically shows how flexible we are with the amount of power which is available to us. We were able to demonstrate a peak charging capability of 261 kilowatts, still working with a connection which is less than 5 kilowatts, which in itself is a feat, if you will. We worked with LEDWP with this pilot, and we had all these results validated with them. These are some images of what exactly did it take to make this installation. It takes a 14,000 GVW forklift to pick it up and put it on a trailer. You strap down onto the trailer, and then you just drop the unit without any actual preparation onto the side to just get it functional. There are 6 operating modes of the system besides it being switched off. In the standby mode, all the telemetry is on, it's consuming electricity, having the system, the Wi-Fi system on. There's the grid charging mode is when we are charging the battery from to the grid. The grid discharging mode is when we are actually feeding energy back to the grid or to a separate load bank. There's a grid charging vehicle charging mode in which we are charging our batteries from the grid and also charging a vehicle. So everything is shared on the same bus. So the power is shared there. And then finally, there's a grid discharging vehicle charging mode in which we are charging the vehicle and also charging back the grid. That is feeding energy back to the grid, where batteries are depleting at the most fast pace. The new variants of the product, we are actually working on V2G systems as well, in which our DC to DC converters are bidirectional, so we can actually draw energy back from the vehicle too. So there'll be separate modes added in which we are actually taking energy out from the vehicle to feed it back to the grid or to store it into our batteries. I wanted to share a little bit of what we learned by building the system, being a very early stage company and with much lesser resources in terms of what the testing operators which we had. We were testing on actual vehicles. In the first 30 days when we started like put the whole system together, our charging profiles, the charging sessions used to fail at the pre-charge stage. So this is the first image. You can see the telemetry data is much spread across. That's why you see a lot of fluctuations here. But whenever we are trying to dump a little bit of current into the vehicle, in the pre-charge phase, that is one of the stages of the handshake with the electric vehicle, you first demonstrate your capability as an EVSE to deliver a specific amount of charge at a specific amount of voltage, so that the vehicle knows that you are a legit EVSE, and then they turn on your contactors. But in this specific case, we are not able to meet exact current window, that is that plus minus 2% or plus minus 5% window. Varies for different automakers. So the vehicle would not let the pre-charge pass, and hence our the current throughput usage drop. And the second scenario is when we are passing the pre-charge, but the vehicle, I will not name the automaker here, but the vehicle is turning on the vehicle contactors, that is turning on its battery just as you hit a specific window. So let's say they're requesting 420 volts and the window is plus minus 60. So even if our charger is at just 380 volts, they will still turn on the contactors because it's in the window. So in that specific scenario, what used to happen is that the vehicle only turned on its batteries and there used to be a backflow into our system. So we are taking energy out of the vehicle, even if that's not intended. Solving that was easy. Finally, this is a specific characteristic graph when there is a continuous power delivery happening into the vehicle. As you can see, there's consistent current happening, but there are some kinks here. That is representative of multiple different kinds of failure which exist. One of them is when there is a specific voltage change which is requested and the DC to DC system is not exactly able to maintain that. Or at times there is the PLC communication loss happens just for a microseconds and the vehicle just starts to freak out and then it's back restored. So there are multiple failures which cause this kind of failures of the system, we were able to get past most of that. At the pilot which we did at Lacey, we demonstrated a peak of 625 amps. I know you'll have questions there. Not all vehicles, not any vehicles can do 625 amps really, at a 261 kilowatt peak speed. The ones in blue are the interoperability testing ones. We generally we were just testing low voltage so that we can just stop charge. So this is pretty much the representative ability, very equivalent to AC charging, right? You're delivering up to 7 miles of range, 12 miles of range, 4 miles of range in around 10 minutes of charging. But you go into like fast charging and extreme fast charging at these red sections, right? In 10 minutes, you are able to deliver up to 134 miles of range into a vehicle. During all of this testing, which happened during almost winter, we did see a lot of peak temperatures happening in Los Angeles during that time. The temperature even went to, at some points of the day, went to much higher than 80 Fahrenheit. And we still did not see any derating of our system. mainly because we're not continuously running these tests. We'll just do this test for a vehicle and for 10 minutes and we'll stop. We did not see any derating of the system, but what we are learning from the field that if we keep running these tests, that is when we will see some kind of degradation. Hopefully not, but probably will. So that basically brings me to the next topic of what exactly is extreme fast charging? How is it different from the current state of DC fast charging infrastructure, and why exactly is required to time cap it, right? Thermal degradation one is one of the things for sure as well. But let me first explain what exactly is XFC, right? It's roughly here in this map. This map kind of compares what exactly different charging standards exist. The CCS charging at up to 400 kilowatts, XFC over CCS charging, the CHAdeMO, the Tesla. The ranges as for example, for the Teslas, the system voltage is roughly around 350 volts. So they are doing 350 to 500 volts. So they're doing a peak of 350 amps. A peak of 400 amps is happening for the typically definition of XFC. So the power delivery is happening at roughly 875 volts, delivering up to 400 amps of current. And we're just like pushing the boundaries of that as well, trying to increase the current as well. Our system's peak capability is 625 amps as well with 1000 volts, but not like at the same time, right? 1000 to 600 is going to be much higher voltages. But what does it mean, right? What does 350 kilowatt of charging means as compared to a 150 kilowatt one? So if you do a 350 kilowatt charging for 10 minutes, it's roughly around 58.3 kilowatt hours. Roughly 12% goes to different losses into the EBSC. That means that around 51 kilowatt hour of capacity is actually available to the car after they have their own losses as well. But just putting that into context for different kind of vehicles, which could vary from 2.2 miles per kilowatt hour to up to 4.2 miles per kilowatt hour, the amount of range which could be delivered into vehicles varies from up to 100 miles to up to 200 miles, and that is just increasing over time right now as the vehicles become more and more efficient. This paradigm of charging is very similar to where exactly gasoline charging is there as well. So gasoline charging, we generally spend around 5 to 7 minutes. That's the data currently. So if we limit first to just simulate a gasoline charging experience, we must limit the length, but it just makes much more business and technical sense. And that is the case which I'm trying to make here. First is when we are time capping the charging sessions, depending on how vehicles behave, that means that the chargers will have high throughput all the time. That is when that means that they'll be operating at the higher capacity which they're designed for, which I'll explain on the next slide. But the second thing is also means that the chargers are much more available. This is a plot of how exactly the average arrival of vehicles versus the peak arrivals happens generally at a gas station. As you can see, if you're just planning for that average arrival, if the peak conditions show up and you are letting people leave their cars there, even if it's a DC fast charger, that means that the chargers would not be available for the next person. But a 10-minute capping of charging session means that even if the peak arrival of vehicles happen close to up to 4 vehicles per day, per hour, that is when people will see and will still have access to it, because even if they arrive and there is somebody else plugged in, they know that the charger will be available for them. It just increases the availability of chargers, just like a gasoline pump. In the technical sense, we will deliver higher miles per charging session, period. And I'll prove that in our next slides. It's just the way batteries behave. And it also will lead to higher longevity of automotive batteries. And that is where is the direction which we'll take in this presentation from now. It's just the traditional sense is that if you're doing extreme fast charging or very fast charging of batteries, automotive batteries degrade fast, which is just factually true. The aging really starts to happen at much later phases of charging when we hit the diffusion limits. And there is some technical data to prove it. So this is a plot of how exactly a Porsche Taycan charges from 0 to 100%. If the battery is completely empty, the charging rates, the peak kilowatts, just go to up to 250. But as the batteries start to fill up, the charging rates keep starting to drop. This is not a traditional CC to CCCV charging. The Porsche is actively making decisions on what exactly is the fastest charging rates. I wouldn't say active; it's kind of passive because it's already decided. It's not actively being decided on for that specific charging session. But if you try to plot that graph into what is the number of miles delivered per 10 minutes of charging over the course of time with the length of charging session, till just picture just becomes much clearer. Uh, the amount of miles which are delivered in just 10 minutes, if you just did charging for first 10 minutes, then we are getting more than 150 miles of range. But if we keep going and to a 40-minute charging session, then the amount of charge which is delivered in that 10 minutes just drops to roughly around 25. For a user to do like a long charging session versus a short one, if they are caring about what is the time they spent at that site, which is generally the case for public charging infrastructure, this is much more bang for their buck, especially for locations where the dwell time is much smaller and the people do not want to wait there. This second plot is credits to Bad Genie. It's in another company spun out of University of Washington. They're working with multiple automakers as well, but their case is that when you're trying to optimize fast charging, the fast charging for shorter times ends in a healthier battery. The two comparisons which are made here is this is conventional CCCV charging, in which you're charging at peak for until you hit SSC and then you do maintain a constant voltage. But their proposed charging algorithm is that you keep maintaining that extreme fast charging at roughly 2C even longer than you hit that constant voltage limit, and then you suddenly drop that voltage, the charging rates, so that the batteries do not degrade as fast. And these are the actual results here. For a fast charging for 2C, the battery, if you continuously do CCCV fast charging for vehicles at 2C, the batteries degrade pretty fast as compared to C/2 charging rate, CCCV. As you can see, the life is much longer. But if you are still charging the vehicles as fast and you are even charging much beyond than the requested SOC, the batteries still have the same life if you just drop the charging rates when the batteries hit those internal diffusion limits. As a limitation on the presentation, I cannot put all those graphs in there, but I'm happy to share the technical presentations which make clear that the diffusion limits, the internal diffusion limits, are the biggest reason why batteries start to degrade. And if you're doing fast charging, it's not about just the fast charging itself, but the length of charging sessions, which causes the biggest degradation in batteries. So finally, the conclusion which I want to make here is time-capped extreme fast charging can really bring gasoline user experience to EV users. The scenarios first is users obviously have to charge frequently because you're not getting a full charge, but it does translate into an efficient miles per minute experience with much lesser waiting times. Currently, if a EV charger is overutilized, it's either under or overutilized. When it's overutilized, you just don't know when exactly that user is going to come and unplug for you to have that charge available. That's something which really needs to be fixed here. The second scenario is that in case of this experience, vehicles will generally arrive at a lower SSC on average because they're just getting a top up. The next time they show up here, they will have a lower SSC, and that translates to a much higher rates of charging because vehicles charge much faster when they're at lower SSC, and that will bolster the same experience in which you only come to charge and there is a lower SSC. And then finally, because of these short charging sessions, the vehicles will experience much lower depth of discharge. Depth of discharge is the cycle which you do to a battery, like where exactly what is the window of state of charge which you're cycling your battery at. And lower depth of discharge is directly correlated to high health of the battery, which pretty much is a known fact into the battery industry. So I hopefully have made my case, and Stephen will take it from here to talk more about what are the parameters of batteries are. and how ReJoule quantifies it.
Hi, everyone. Yeah, thanks for that talk, Anurag. Really interesting stuff. And it's really cool to see all the progress that ElectricFish has made over the years. So now I'll be discussing some of the implications on battery health. With a caveat, I won't go so far as supporting claims on whether extreme fast charging is detrimental or is not detrimental to battery health. We just don't have that data to support it. And we are a data-driven company, so I won't be saying anything like that. But I will be looking at some implications of what some of the things that Anurag is saying, as well as just defining what battery degradation is really, and giving some basic definitions, because what we've learned is that automakers, battery manufacturers, everyone really has a slightly different definition of SOH, SOC, and all that. And we'll look at some different methods to assess battery degradation. We'll be reserving questions for after this short presentation. So if you've already typed a question into the box, please sit tight. We'll get to you shortly. Can everyone see my screen, by the way? It should be ReJoule implications on battery degradation and health. So let's first talk a bit about ReJoule. We are a Southern California-based startup, and we help customers maximize the value of their batteries through insightful data analytics and rapid battery health diagnostics. I'm Stephen, the co-founder and CEO, and have a co-founder, Zora, who's the CFO. We also have a team of advisors with automotive, energy, and software backgrounds helping us out on our startup. We're supported by the National Science Foundation, Department of Energy, and the California Energy Commission. And we're also one of the winners of GAMIC, the Global Automotive Mobility Innovation Challenge, last year. We're currently participating in the Black & Veatch Ignite X Accelerator program. So going back to that big question, the big problem that Anurag was talking about, we're going to need a lot more fast charging. We're going to need a lot more energy infrastructure, and we're going to need a lot of batteries. And so ReJoule is asking the question, what's going to happen to all those batteries when they retire from the vehicles? There's a McKinsey study that by 2030, there can potentially be more used battery supply than grid demand for energy storage. And that's a crazy stat to think about. And considering where right now the battery reuse marketplace is only really a small niche DIY community, a lot of off-grid storage, there's a long way to go before we can fully realize a battery repurposing marketplace. So there's a lot of value to unlock in that space. There's also some regulatory headwinds that we're paying very close attention to. If you're not familiar, extended producer responsibility, EPR, is coming, and EPR will put financial and collection burden on producers of products with batteries to finance the collection and recycling of these batteries. And that may fundamentally change how automakers make money, the business models of a lot of these companies. There's also the California Air Resources Board, which will be, they're looking at mandating battery durability testing and warranty enforcement. So I believe that those who tackle Advanced Clean Cars 2 from CARB and EPR and some of these other regulatory trends head on will not only pay less to meet regulation, they'll also find other revenue streams like repurposing and energy as a service. And it's a challenge that can be profitable, but it has to be handled appropriately. And the problem is that there's currently no cost-effective means to assess battery health today. There are, in vehicles and stationary storage systems, there's onboard algorithms, but those are often inaccurate. Some may vary up to 15% as that battery degrades. Then you have measurement, which the state of the art today is essentially charging and discharging these batteries And that can take several hours, 6 to 10 hours of testing. And for large battery packs, high voltage battery packs, it requires some specialized heavy equipment. So if you can't really scale that when we're talking about millions of electric vehicles on our roads. So ReJoule is offering a product that can make state of health measurement accurate and painless. This is a product where you can plug this device into the vehicle charging port. We can perform a pack level measurement in less than 5 minutes, and we can get a state of health prediction on that battery pack with less than 2% error. We have a number of patents that cover everything from the hardware that's taking the measurement to some of the signal processing and software that is processing and making sense of these measurements. And finally, we have some proprietary machine learning modeling algorithms that we've worked on for a number of batteries now. ReJoule is building a cloud-based data platform specifically for state of health modeling. And this platform can help aggregate data from various sources, including EVs, test equipment, and our own high voltage EIS devices. And in this data platform, we are able to ingest, clean, transform, and featureize a lot of the data to train our battery models. And finally, we have some existing Second Life battery projects, 2 of which are funded by the California Energy Commission. We plan to have about 1 megawatt hours of batteries deployed in the in SoCal Edison and San Diego Gas and Electric utilities for some CNI building energy storage before the end of the year. And we're working with some key partners on these projects. Okay, so let's dig a bit deeper into what is battery degradation really? As I said before, everyone seems to have different definitions for how to measure this. So from let's look at some key words that may define battery degradation. You may hear state of health a lot, capacity, energy, energy throughput, internal resistance, impedance, state of charge. The thing to remember though is that all of these parameters are calculated or inferred. None of these can actually be measured. The only measurable parameters are voltage, current, temperature, and pressure. And temperature is, I have a little asterisk there because we're usually putting some thermistors, thermocouples on the periphery of a battery and predicting an internal temperature of the battery. So really it comes down to voltage and current a lot of times when we're talking about measurements. And since we're only looking at voltage and current, it really comes down to Ohm's law and voltage windows. And let's get into that a bit. So with Ohm's law, we've done some studies on battery degradation, where we're able to see that the AC impedance of batteries does increase over time. This is something that's well known. And here you can see a plot for a nickel NMC battery, nickel manganese cobalt battery cell, which we've done some accelerated aging over a number of weeks, and we saw that AC impedance, the Nyquist plot, grow. We're able to model this through traditional equivalent circuit models, and we're able to see how some of these circuit parameters grow over time as the battery ages. And so if you're looking at from a pure voltage current impedance perspective, you just apply Ohm's law and you can see how the battery may perform over time. So when we're looking at voltage windows, here is because we're able to look at aged batteries through our Second Life battery projects, this plot you can see how a circuit, how an OCV to normalized discharge capacity curve changes over time as the battery ages. So each of these colored plots is a different state of health for the same cell, essentially. And what you see is indeed, this voltage curve does change over time. And you can also see that about 80% of the energy of this discharge curve is within about a 300 millivolt window. And so, if you adjust the top end or the bottom end of this voltage window, you're essentially unlocking more and more discharge capacity as you increase it. And if you decrease that voltage window, you have less capacity. And this is essentially what a lot of automakers are doing already. Tesla famously unlocked additional range for some of their customers a number of years back to help them escape the hurricane conditions. They weren't adding additional energy into the batteries. They're simply doing a software update where they were increasing these voltage windows. So from a measurement perspective, since we can only measure voltage, this voltage window becomes very, very important when we're talking about how much discharge capacity or charge capacity is there in a battery pack. And we can also look at how high C rates can affect these, the amount of energy that a battery is able to discharge from these voltage windows. So you can see here, this is another study on an NMC cell. And again, each of these colored plots is the same cell, but at different state of health. And in each of these curves, the battery was subject to a 3C discharge. You can see when the battery is healthy, there's a fair amount of 2.8 amp hours of capacity on that fresh battery. But once you get more and more aged, this DC internal resistance really kicks in the very beginning of that discharge, and it quickly drops off, so you get less and less energy. So when we're talking about extreme fast charging, 6C charge rates, 5C charge rates, what we expect is that this DCIR will have a huge impact for aged batteries. And what will end up happening is for these aged and imbalanced battery packs, the peak current allowed will have to be limited because of that high DCIR. Okay, so because we're doing a lot of second life battery projects, we also had the ability to look at aged battery modules and kind of see the state of imbalance of these modules as they age. So you can see in this plot, there's essentially 3 different battery modules, okay? In the green, there's a battery module where each of the cells are essentially 100%. In the yellow, each of the battery module on average is 88% state of health. And that red curve, that group of red curves, that's a single battery module with cells on average of 75% SOH. And where this becomes really interesting is as the batteries age, you can see more and more divergence in the usable capacity when you're thinking about that voltage window. If we keep that voltage window constant, then you start to be limited by that weakest battery. And in this fresh battery module, you essentially have very, very close agreement in the discharge capacity of each cell. As that battery ages, about 88%, we saw a 9% delta in the discharge capacity from the strongest cell to the weakest cell in that particular module. And then when that battery is very aged, 75%, we saw up to a 15% difference in the discharge capacity from the strongest cell to the weakest cell. Keep in mind, all the cells in that red curve, they're from the exact same battery module from the same vehicle. So that means that as we age, we're really going to see imbalance causing a lot of problems for the discharge capacity of batteries. generally, that was already known. That's how a lot of battery management systems are designed. But here we have some real data of real aged batteries and how that can affect the discharge capacity. I also want to, everyone should keep in mind that the battery packs we're looking at for repurposing, this is old technology. These are old cells. The pack designs are now outdated. Battery management systems and charging algorithms are all outdated. And so we do expect that next generation of used batteries to be much more tightly controlled, and therefore we expect the degradation to be less between cells in a module moving forward, but it's still something that needs to be looked at, right? We've done some testing on when we look at stacking cells and modules in series, how that might affect the voltage windows and the discharge curves. And you can see there's three sets of, actually 4 sets of batteries here. And for the batteries that start at a relatively low SOC, you see a huge variation in the voltage, about 100 millivolts between cells in this stack. But as you charge them all up, where that voltage curve is flatter, you start to see less and less of an imbalance in the cells within those modules. And then finally, when you're towards the middle of the SOC range, 25% to 80%, that imbalance in voltage at least gets even smaller. So you really want to stay away from the extremes of that voltage window, especially as those batteries degrade. Okay. Finally, does extreme fast charging accelerate degradation? So here, some of the data we show is we didn't do extreme fast charging. We actually did high discharge rates here. And we ran a design of experiments, a DOE, where we looked at a number of different parameters that would affect battery degradation. We found that depth of discharge, DOD, has the biggest impact on how the batteries degrade. So back to my previous statement, you want to really limit the low end of the, make sure that the battery doesn't get to the low end of the discharge curve too often, because we found that to be the biggest effect, to have the biggest effect on the degradation of the batteries. Next was temperature. We want to keep the temperature, or the temperature of the batteries and the cells in a respectable range between 5 degrees C up to maybe 40 degrees C. We don't want to get it too hot. Where we saw high current rates having an effect was only when multiplied with the temperature. And so this does back up Anurag's statement from before, where you can have high discharge rates, but for short periods of time, because you don't want the cells to begin to heat up and really start to degrade those batteries. Now, based on what I've said here, I can say high current rates is possible, but we'll have to look at different cells. This study in particular was an NMC cell. It was a commercial 18650, and these what parameters affect degradation and how much each parameter affects degradation will depend between chemistries. It'll depend between usage patterns and vehicle designs. Oh, and if you're wondering about this plot, why there was so much jaggedness, we just had some bad connectors. We fixed that in our subsequent studies. Okay, so some takeaways is that extreme fast charging is possible, but not as a rule. We really have to look at a lot of different things to understand whether it'll affect degradation and really by how much. We know batteries degrade, and we just need to make sure that the BMS we design, the charging profiles, usage rates, all that are taken into account before we can definitively say that extreme fast charging is possible for a lot of batteries. The next thing is we need to monitor, measure everything, and only by monitoring a lot of different things over a big period of time can you, definitively make claims about battery degradation. And lastly, it's the takeaway is that good data is more important than big data. So we're not just saying monitor voltages on the millisecond range for every cell and every vehicle. That's too much data. But what we do want is to have, we want to be able to measure the salient parameters that do affect battery degradation. And we're offering some products and services to help with that monitoring. And with that, thank you. And we'll now be opening it up to questions. So I will stop sharing my screen, and we're going to go in order of when the questions were asked. Okay, so the first question is from Surinder Singh for Anurag. What kind of permits or certifications have you had to go through?
Thanks for the question, Surinder. So there's two-pronged answers. For our first pilot deployment, our site host, the DWP and Lacey, was super comfortable with us to just repurpose the existing electrical port, which was there outside. We wanted a 40 kilowatt connection, but we just worked with a 5 kilowatt one. So there was no electrical permits, which is required because we did not put any new wires. They were existingly there. For the city approval, the second one is generally city and AHJs, that is the fire marshals. We did not have to do that for the specific site because we looked for it like it was a temporary installation, and the site owner who owned the building gave us that approval to just deploy that. It was a private installation, not a public facing one. But in general, when we are going forward, we're doing installations in our public sites like convenience stores, gas stations, or even fleet operators. As long as it is a public-facing installations, there are two major stakeholders which we must make comfortable. First is the electrical utility. They need to give us a permit that if it's a single unidirectional connection, that generates an off-the-shelf permit for a single-phase connection. But if you want to do a bidirectional one, that is you actually feed energy or refuel the grid back, then you have to go through a more arduous process, and not all states have that ability. DD certainly does. We are planning for pilot there. And the second one is basically the AHJ authorities with jurisdiction. You have to get a city permit. The city gives an approval on where exactly you're placing it. How far is it from the curb? Is it accessible? Is it gonna affect the traffic flow? And a sub permit of that is the approval from a fire safety marshal. And generally, to make them comfortable, you need to have a UO certification. The 9540 is one of the biggest ones. Or you can have your own assessment if you are working as closely with AHJ, if you have a security perimeter plan. So our unit, we plan to get the UO 9540 by end of this year. Currently, all the deployments which are putting over this year, around 6 of them, we are individually working with AHJ so that we can make them comfortable for the fire safety of the unit. So I hope that answers it.
Okay, very cool. Okay, next question is from Bill Shellman. For Anurag, how does the user know to stop the extreme fast charging after a short time to optimize the range and battery life?
Yeah, so apologies, I could not express that. That is our business model. We are not selling the hardware, we are operating this. Whenever we deploy these units, we either lease it out, or even if we sell it up front, we are managing this as a research through a SaaS subscription model. So the way we do it is we time cap the charging session itself to just 10 minutes. So the users are aware that it is a session-based pricing, which is obviously derived from a kilowatt hour delivered. But at that end of the 10 minutes, the charging sessions will stop. you will have to like, if the traction in that site is much lower and there's nobody else following, generally from historic data, if we learn that, then we can let users start the sessions again, but it's just time cap regarding from the EBSE itself. The users do not have to do that.
Okay, great. Next question from Len Kata. Let's see. Is there any effort to reduce charging time and increase vehicle, or sorry, that wasn't the question, trying to read it.
I can just quickly comment on, I think it's not a question from Len.
Yeah.
She just made a comment that the gasolines as
Okay,
are regulated to be 10 gallons per minute, which means around 400 miles of range in just 2 minutes. That's definitely a data point. I think we just collected the data ourselves that not all gas stations have that 10 gal per min the capability at times. You have just like in other places where they do not go as fast, as well as we must consider how much time does it take to actually go through the whole payment process. With EV charging, and with the plug-in charge protocol, we can really drastically cut the amount of time which users spend trying to go through the payment process. You can just come, plug in, and the vehicle starts to charge. And then that will cut time further from as compared to a gasoline fueling experience. But yeah, point taken there, man.
Okay, yeah, cool. Yeah, I see that wasn't exactly a question, but more a comment. Okay, the next question is again from Surinder Singh. Is the 2% accuracy, or 2% accuracy is great. What are the conditions for that accuracy, and how does that change with variables, chemistry, etc.? That's a question for me. So yeah, thanks for that question, Surinder. So the conditions for that is, and first of all, we're doing this with repurposed batteries, and so we've now proven this model on a number of LFP cells and modules from various manufacturers, as well as some NMC and LMO batteries. And the conditions for that is we did essentially a benchmarking study where we gathered data from samples of between 30 batteries all the way up to 500 batteries, depending on the batteries that we can get. And with those batteries, we did benchmarking for capacity, so just a 1/3 C discharge and charge. And then we also gathered our EIS measurements. And with this is a machine learning model, and so with all machine learning models, there's a training set and a test set where 80% was 80% of the data was used to train our model, and then we tested on the remaining 2% or the remaining 20% of the data. And so once we've trained the model, we compared our EIS prediction on battery capacity against that benchmarked 1/3 discharge rate capacity test. And again, we've done this on a number of battery chemistries, cells, modules as well. The next thing we're going to do is to do this for battery packs. Okay, we got another question from Francisco. What are the primary use cases and incentives for bidirectional grid powering? Is this made more for blackouts and unreliability, or made to work with the grid providers? Anurag?
Yeah, thanks, Stephen. That's a great question. The primary use case for the bidirectional grid routing varies on where exactly you are at. Trying to power blackouts right from the beginning, when we have just few units deployed, is not something which is feasible right away, nor the utilities are super comfortable for us to actually eliminate the feeders. There are much stringent requirements in which if the grid is broken down, then there is probably a grid worker is trying to fix it, and it must be de-energized. So there are much stringent requirements in terms of data collection, what exactly is the automatic transfer switch, which is disconnecting that asset. And we are a little further away from getting a contract with utility in which we can actually execute it. There are some specific feeders in territories like Southern California, even in I think Seattle, in which there are some isolated feeders, like sort of a test systems, in which we can try to have one or two of our units there and eliminate that feeder which is isolated from the rest of the grid, just to demonstrate this capability. And there are some companies like Veritone who do have pilots like big utilities to do that. But currently, what the primary use case which we are serving with the same capability which enables this blackout powering is just to participate in energy arbitrage services, that is demand response, and also programs like emergency load reduction, in which you cut the load from to the electricity grid when the grid is super stressed, and you get that communication using the open ADI protocol, or there are some specific protocols which are used specifically. We are doing a pilot with the utility in the Michigan area to demonstrate this capability. But the second thing is you can also curtail the loads locally, right? You don't even have to be on the meter. So there's on the meter and behind the meter, in which are you directly feeding energy back to the grid, the meter goes backwards. You don't even have to do that. It could be the case that you have got a big hospital in which it has some specific peak loads, or let's say in terms of a gas station, there is a car wash which has some peaky loads, right? You can sit just behind the meter, and each of these units can power those specific peak loads so that loads do not show up on the electricity meter itself. So there are multiple mechanisms in which you can do that. Being an early stage startup in which we are only have a few deployments going, we are working directly with energy aggregators. These are the companies which have already bid into the program from utilities, bidding up to hundreds of megawatts of capacity. They already have contracts, and they take our assets, integrate it into the portfolio which they have, so that they can aggregate all of this load and cut that load, and then get paid by utilities, keep a percentage, and pay us. So sort of a long cold answer. Hopefully that answers it. Francisco.
All right. Let's see. Next question is from Bill. A great question here. Has the extreme fast charge unit been used in wintertime cold temperatures? And if so, how did it perform?
Love that. So we were deployed in winter time, but it was in Los Angeles, so it was pretty hard there. But we are taking the unit to a winter region. The next build outs are planned to be deployed in extreme situations. We actually have to create a tiny variant of the product so that it can work in much higher temperatures like Arizona and temperatures like Alaska. But we will have that answer for you by this time next year. Because one of our deployments will be live at cold state over the course of next few months.
Yeah, it was cold for LA standards, but not cold for everyone else.
Yep.
Okay, next question from Mario. What's the status of developing under road service charging while vehicles drive on roads?
Personally, I love that technology. I think there's a great use case for it. Inductive charging is pretty much getting there. I think there's a street being built in Michigan which does inductive charging as well. And I think when we're trying to simulate this 10-minute charging experience, it doesn't have to be wired, right? If you are going through a drive-through at a food station, like in and out, or Burger King. When you're waiting for those 10 minutes driving and waiting for your food, that line could be energized and you can get charged during that time. So I love that use case. That is not something which we're doing here at ElectricFish, maybe down the line, but I love that use case. Yeah.
Okay, cool. And Anurag, I have a question for you actually. So what do you think is the primary value in your business? Is it the hardware? Is it the siting, the optimization engine, or is it something completely different?
Great. Thanks for the question, Stephen. I think it's the integration of everything which is bringing value. Obviously, we have that baked into our hardware itself. We are spending and hiring a lot of data scientists so that we can build a lot of PROs on the source code data too. And the optimization engine is something which will be tested real time, because each of our units must show the ROI which we promised to our customers, right? We plan to get up to 3x ROI of each of our units. So yeah, each of this is going to be tested. But if the hardware doesn't work all the time, it's not going to be great as well. So yeah, thanks for that question. But all of this is important, Stephen. Well, we are almost at the end. But Stephen, I did want for you to like just explain a little bit on how exactly you work with different automakers in terms of how long would it take you to build a SOH model if you do your EIS testing as well.
Yeah. So I think one of the big advantages of our technology is that we don't need thousands of samples to build a good model. And when I say good model, it's essentially being able to predict SOH with less than 2% accuracy. We have worked with batteries in the past where we've had as little as 30 samples, and we were able to get something less than 3% error in our SOH prediction. Obviously, the more samples we have, as with any machine learning or just statistics problem, then we can get more accurate in our modeling. But we've worked with as little as 30, and we typically are between 50 to about 100 battery samples. Yeah, and how we work with automakers, it's those samples were modules or cells. Delivering packs to do testing on is much more challenging, and so with that we are finding different ways to deploy our units in the field so that we can access vehicles without having to tie up 50 vehicles just for some testing.
That's great.
Okay, and then really quickly to answer Surendra's question, the 30 samples were cycled once each. So these were already aged, and so we cycled about once, maybe twice if there was a bad test. So Francisco had a question as well. One question about the use of machine learning in battery life analysis is this model made to be used for outside applications, or is it planned to be implemented in the BMS? The level of hardware, or what level of hardware is required for it? Yeah, Francisco, that's a great question. And we're looking at two different markets, and depending on what market, that would kind of change the equation. So when we're looking at battery repurposing, second life, a lot of these batteries have already been removed from the vehicles, and that way we have a device that would just plug into the plus and minus terminals. If there is a BMS involved, then we would connect to that BMS to grab additional cell level data. The other use case is for when the batteries are still inside the vehicle. And that's the application I showed in my presentation, where we have a device outside of the vehicle and we plug into the charging port. We're working with an automaker to figure out some of the handshaking that's going on, and in that case, we would leverage the existing BMS hardware and have some additional software that goes inside the vehicle. And that way, the hardware and the software is kind of decoupled. We don't need to add additional hardware into the vehicle to make that work. Okay, if there's no more questions, we're about 5 minutes over, which I've been told is the cutoff. So thank you, everybody. And just as a reminder, this video recording will be made available on the SAE Detroit section's YouTube channel at a later date, so look out for that. And thank you, everyone. Thank you, everyone, for joining. It's really cool to talk to you, Anurag.
Same here, Stephen. Excellent. Bye.
Bye, everyone.